This is my Quideo number 4. My name is Tyler. Alright, let's start off with a basic question. This is from the Gallup poll, and they want to find out how many adults attended church or synagogue during the past week. It also gives you that you're supposed to suppose that 40% of the adult population did attend, and they have an SRS size of 1785, and they want to know whether it would come within plus or minus 3 percentage points of this true value. So start off point A. If the proportion of if the p hat is a proportion of the sample who did attend church or synagogue, what is the mean of the sampling distribution of p hat, and what is the standard deviation? So the mean of a sampling distribution is actually equal to the population proportion. So p is going to equal 0.4 because that's given in the problem, which is going to be 40% of the adult population that did attend. So, and then you move on to your standard deviation, and your formula for that would be square root of p times 1 minus p over n. So you have your p, which is 0.4, and then 1 minus p is 0.6, divided by your n, which is 1785. You're going to get 0.0116 for your standard deviation. Part B of this question wants you to explain why you can use the formula for standard deviation of p hat in this setting. Well, this is easy to explain if you know your rule of thumbs. And your first rule of thumb is that when you use the formula for the standard deviation of p hat, only when the size of population is at least 10 times as large as the sample size. So the population of all US adults is obviously at least 10 times as large as the sample population, to 1,785 adults surveyed in this question. Okay, so part C of this question wants you to check that you can use a normal approximation for the distribution of p hat for your rule of thumb 2. And if you know your rule of thumb 2, it states that the normal approximation for the distribution of p hat can be used when np is greater than or equal to 10 and nq is greater than or equal to 10 are satisfied. So for your np, it would be, since your n is 1785 and your p is 0.4, because we know that already, you would multiply those two together, and it would be 714, which is obviously greater than 10. And then for your nq, it would be 0.6 for your q and 1785 for your n, because you already know that. So when you multiply those two together, you're going to get 1071, which is obviously greater than 10. So that one's pretty simple. For part D of this problem, it wants you to find the probability that p hat takes a value between 0.37 and 0.43, and it wants you to use an SRS size of 1785, which we've been using. They usually give a result p hat within plus or minus 3 percentage points of the true population proportion. So then it wants you to explain how you're going to find all this. So first, start off with my z-score formula over here, which is x minus u over o, which is standard deviation like we've been using. So I plug it into the proportion over here and get 0.37 is less than p hat, which is less than 0.43, which was given in the problem. And then you're going to plug those numbers into your z-scores and put them into the equation. So once you do all that, it'll come over here and you get negative 2.586 and positive 2.586, which are going to be your z-scores. So, and then what you do with them is you go to your table in the front of your book to find your proportion values, and you get 0.0049 and 0.995. And then what you do with those is you're going to write your conclusion at the bottom. You can obviously conclude that over 99% of the sample should give p hat within 3 plus or minus 3 percentage points of the population proportion, which is going to be 99%. And obviously these are within 3 percentage points of that. Okay, moving on to your advanced question, which is about researchers who are interested in comparing two methods for estimating tire wear. And the first method used was for the amount of weight lost by a tire, and the second was about the amount of wear in the grooves of the tire. So they used a random sample of 16 tires, and both methods were used to estimate the total distance traveled by each tire. And then this is all explained in the table below. So part A, this question wants you to construct and interpret a 95% confidence interval for the mean difference u in the estimates from the two methods in the population of tires. Come over here to my part A. So what you're going to use for this question is a one sample t-test, and you're going to need your confidence interval formula as well, which is going to be x bar plus or minus t times s over square root of n. Now, in order to find your t star for this question, which is going to be 2.131, you're going to need to find your degrees of freedom, which is n minus 1, and your n in this problem is 16. So you can do 16 minus 1, which is going to be 15. You can use table C in the back of your textbook and come over here. But since it's 16 minus 1, it's going to be 15, so you're going to use 15. And then you're going to move on over until you get a value where it's going to be equal to 95%, because that's what you're looking for. You can come over here and get 2.131, which is going to be 95% confidence level. So that's going to be your t star. Now moving on to part B of this question, it wants to know, does your interval in part A give convincing evidence of a difference in the two methods of estimating tire wear? So, based on our interval in part A, which is 2.837 to 6.275, excuse me, we can conclude that there is convincing evidence that there's a difference in the two methods of estimating tire wear. The difference between the two is not 0. It's not equal to 0. So there's a positive range of numbers. Okay, now moving on to the AP question, which is dealing with golf balls and standards and what they must be used in professional tournaments, yada, 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 all that kind of stuff. Pretty much what you can take away from that is the 291.2 yards can't exceed that. They don't want the ball to travel further than that. So, part A of this question asks, if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a ball that is randomly selected for testing will travel too far? So over here, I just use D is going to be equal to my distance, and it gives you your standard deviation, which is O, which is going to be 2.8 yards, and then I have my z-score formula, and my x-bar, which is 291.2 yards, which is the mean that it can't exceed. So I just kind of wrote some notes down there, so just so I have an idea going into this problem. And I set up my proportion. I start over here, where D is going to be greater than 291.2, which is the yards that it can't exceed, but in this problem it wants to travel 288 yards. So come over here, I'm going to plug in my z-score formula, and it's going to be 291.2 minus 288 divided by 2.8, which is your standard deviation, and then for that you're going to get 1.14. But that's not done yet. In order to find your z-score, you're going to need to go to your table A in the front of the book, and that's once you plug that into there, find that, it's going to be 0.8729. And then, since we're trying to find the mean distance traveled to be equal to 288 yards, we're going to subtract that number from 1, so we're going to get 0.1271, which is going to be our proportion. So the probability a ball is randomly selected for testing will travel too far is 0.1271, which would be 12.71%. Part B of this question wants you to assume the mean distance traveled is 288 yards and that 5 balls are independently tested. So then it wants you to find what the probability is that at least one of the 5 balls will exceed the maximum distance of 291.2 yards. Over here I just wrote some side notes again. D equals distance, and 1D is one of the balls exceeds 288 yards, and then 5D is going to be that all 5 distances exceed 500 or 288 yards. So over here I come to my equation, and it's going to be P 1D is greater than 291.2 yards equals 1 minus P times 5 distances is less than or equal to 291.2 yards. So 1 minus P times 1 minus 0.1271, which you're getting from the equation in part A, excuse me. And then you're going to raise that to the 5th power because you're trying to find 5 distances. And then once you get that, or once you do 1 minus 0.127271, it's going to be 0.8729. Then you're going to put that to the 5th power, and you're going to get 0.5068, and then you subtract that from 1 and get 0.4932. So the probability that at least one of the 5 balls exceeds the maximum distance of 291.2 yards is 0.4932, or 49.32%. Now moving on to part C, it says if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum difference or distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process? So to start off, I tried to find the z-score for 99%, which you're going to use table A in the front of your book. and your 99% standard normal distribution z-score is 2.33. So over here I just wrote some more side notes of what I have. My z-score is 2.33, and my x-bar, which is the mean, is going to be 291.2 yards, and my standard deviation is 2.8 still. So you're kind of working backwards on this problem. So you're going to have 2.33, which is your z-score, equals 291.2 minus unknown number, which we're trying to find, divided by our standard deviation of 2.8. So after you work backwards from this with your basic math, you're going to find that your largest mean is going to turn out to be 284.676. Over here I wrote my statement. So if the manufacturer wants to be 99% certain a random ball won't exceed the maximum distance of 291.2 yards, the largest mean that can be used in the manufacturing process is going to be 284.676 yards.